Welcome to Sleepy Science Tales. It's lovely to have you with us this evening. Before we begin, you might gently notice where you are listening from tonight. A quiet bedroom with a soft lamp, a late train with the world humming beyond the window, a couch that has learned the shape of your resting shoulders, maybe a pillow that feels like it has been waiting for you. Wherever you are, I hope you feel safe, warm enough, and unhurried. If you enjoy these calm explorations, you can always leave a simple comment telling us where you are in the world. It is a small thing, but it makes this sleepy little community feel connected, like distant lights on a coastline, all glowing at once. And now, we will do something gently ambitious. We will wander into quantum physics, but we will do it slowly, softly, and without effort. I will try not to make it so interesting that it wakes you up. But if it does, that is all right. You can trade a little extra wakefulness for a quieter understanding of why light sometimes behaves like a ripple, why particles sometimes behave like possibilities, and why nature, at its smallest scales, can feel like it is thinking in a language we do not speak. A fair trade on a restful night. So, let us begin. Quantum physics is the study of the very small. Not small like a grain of sand. Not small like a speck of dust. Small like the inner architecture of atoms, where what seems solid becomes airy, where certainty becomes a soft blur, and where the world behaves less like a tidy machine and more like a gentle cloud of maybes. In the everyday world, things feel reliable. A cup falls when you let go. A door stays closed until you open it. A coin lands one way or the other. But a little more than a century ago, scientists began to look closer, much closer. And the closer they looked, the less the universe behaved like the common sense we grew up with. Light refused to be only a wave. It also behaved like a particle. Particles refused to be only little objects. They also behaved like waves. And in some cases, it seemed that the act of measuring was not just reading a result, but shaping which result was allowed to appear. That last idea can sound dramatic, so we will hold it gently. We will not force it into a slogan. We will just let it rest in the background, like distant music, while we learn the slower story underneath. Because quantum physics did not arrive all at once. It arrived the way dawn arrives, quietly, in small changes that only become obvious when you look back. At the turn of the 20th century, physics felt nearly complete. The laws of motion were elegant. Heat and energy seemed understood. Electricity and magnetism had been woven together into a beautiful set of ideas that described light itself. There was confidence in the air, a sense that the universe had been mostly explained and that the remaining problems were just small details, like dust in the corners of a bright room. One of those corners involved a very ordinary experience. Heat something, and it glows. A stove ring turns red. A piece of metal becomes orange, then pale, then white. A campfire shifts in color as it breathes and settles. This glow is not just pretty. It is radiation, light and heat flowing outward from warm matter. Scientists call an idealized version of this glow blackbody radiation not because it is dark, but because it is a perfect absorber and emitter, a simple model for the way warm objects shine. It seemed like a problem that should have yielded easily. But the mathematics misbehaved. Classical physics predicted that as an object became hotter, it should pour out more and more energy at shorter and shorter wavelengths, especially in the ultraviolet range. And the formula did not merely predict a lot of ultraviolet light. It predicted something absurd. It predicted infinite energy. And infinity is a red flag in physics. It is usually the sound the universe makes when our assumptions are wrong. This particular mismatch between mathematics and reality became known by a memorable name: the ultraviolet catastrophe. A catastrophe not in the lab, but on the page. No matter how the equations were rearranged, the classical picture kept insisting on impossibilities. But the real world did not do that. A hot object does not emit infinite energy. It simply glows, calmly, within limits. So something was missing. And then a physicist named Max Planck took a careful step. Planck was not trying to be poetic. He was trying to be practical. He wanted the numbers to behave. He wanted the curve in the math to match the curve measured in experiments. So he tried a small, strange idea. What if energy could not be emitted in any amount at all? What if, instead, energy came in tiny packets? Not infinitely divisible, not smooth like a continuous stream, but stepwise, like coins rather than water. If you have coins, you can pay in 1 coin, or 2, or 3. But you cannot pay in half a coin without changing what money means. Planck proposed that energy might behave in a similar way. It might come in minimum-sized packets. He called these packets quanta, and he introduced a small constant to set the scale of this packet size. It was unimaginably tiny, but it made the equations beautifully well behaved. When he used this idea, the ultraviolet catastrophe disappeared. The math came back down to earth. It matched the real world. In a quiet moment, with a gentle adjustment, Planck had placed the first stone on a path that would become quantum theory. And the strange part is, he did not fully trust what he had done. At first, Planck treated it like a clever fix, a mathematical convenience, a temporary bridge over a problem, not a new description of the universe. But the bridge held, and other minds began to walk across it. Because once you allow energy to arrive in packets, it becomes easier to understand another stubborn puzzle, one that involves metal, light, and electrons. Imagine a metal surface. Shine light onto it. If the light is energetic enough, electrons can be knocked free from the metal, like tiny beads popped loose from a surface. This is called the photoelectric effect. At first, it seems straightforward. Light brings energy. Energy frees electrons. So classical thinking made a simple prediction. Increase the brightness of the light, and the ejected electrons should fly out with more energy. A brighter wave should shake harder, like stronger wind on a field of tall grass. But experiments did not agree. Brightness was not the key. Frequency was. If the light was below a certain frequency, nothing happened. You could shine a very bright light, and the electrons stayed put. But if the light was above a certain frequency, electrons popped out easily, even when the light was dim. There was a threshold, a hard line, a rule. And classical wave theory could not explain that rule. Then Albert Einstein offered a bold suggestion. What if light sometimes arrives as discrete packets of energy? Not just energy in packets, but light itself as packets. Little bundles, each carrying an amount of energy tied to its frequency. If a single packet does not carry enough energy, it cannot free an electron. No amount of brightness changes that, because brightness only adds more packets, not more energy per packet. It is like trying to open a door with keys. If the keys are the wrong shape, Bringing 1,000 of them does not help. You need one key that fits. Einstein's idea fit the experiments perfectly. Those packets came to be called photons. And just like that, light was no longer only a wave. It was also particle-like. This is one of the first places quantum physics asks us to relax our habits. In daily life, we like categories. A thing is either this or that, wave or particle, here or there, on or off. Quantum physics suggests that nature does not always choose a single category for our comfort. Light can spread like a wave, making interference patterns like ripples on a pond. And it can land like a particle, arriving in individual impacts, each one with a definite bundle of energy. If you are listening for sleep, you do not need to hold the whole paradox tightly. You can treat it like a slow image. Light is a ripple that sometimes arrives as a drop, a smooth motion that sometimes arrives in steps. And if your mind wanders here, that is fine. Let it wander. Quantum ideas are not meant to be gripped like a steering wheel. They are meant to be floated like a leaf on water. Einstein's photon explanation was so important that it later earned him a Nobel Prize, not for relativity, but for this work on light and electrons. And still, even Einstein found the deeper implications of quantum theory unsettling. He liked a universe that felt orderly and complete, where things had definite properties whether we were watching or not. Quantum physics kept leaning in the other direction. And to see just how strange that direction can become, there is an experiment so simple it almost feels like a trick, and yet it is one of the clearest windows into the quantum world. The double slit experiment. Imagine a barrier with two narrow slits cut into it. Behind the barrier, a screen. You shine light through the slits toward the screen and watch what pattern forms. If light behaves like a wave, the waves passing through the two slits overlap and interfere. Peaks reinforce peaks, troughs cancel peaks, and the screen shows a pattern of bright and dark bands. If light behaves like particles, like tiny bullets, you would expect two bright clusters behind the slits, because each particle would pass through one slit or the other and land. When you do the experiment with ordinary light, you see the wave pattern, the interference bands. No surprise. But then, the experiment becomes whisper quiet. The light is dimmed until it releases photons one at a time. Not a stream, but single arrivals, spaced out patiently. Now you might expect the photons to behave like particles. One photon goes through one slit, lands on the screen, makes one dot. And at first, that is what you see. Individual dots. Little impacts. But as you collect more and more dots over time, something strange happens. The dots do not form two clusters. They slowly build the interference pattern, the wave pattern, as if each single photon, arriving alone, still somehow behaves like a wave passing through both slits. It is not that the photon splits into two smaller photons. It is not that there are secretly many photons. It is one, and yet the pattern suggests it is exploring possibilities like a wave. And then, with a kind of quiet drama, you add a detector. You try to check which slit the photon goes through. Just a gentle check, just an attempt to look. And when you do, the interference pattern disappears. The photons behave like particles again. Two clusters. No bands. It is as if nature changes its behavior depending on whether the path information exists. That can sound like the universe performs for an audience, but we will handle it more carefully. One way to hold it is this. Quantum systems do not always have a single definite story until an interaction forces one story to be chosen. Before measurement, the system is described by a wave of possibilities. After measurement, one outcome is selected. And the double slit experiment is a simple stage where that selection becomes visible. If your mind starts to wake up here, soften your focus. You do not need to solve it. You only need to let the idea pass by. At the smallest scales, reality can behave like a set of overlapping options, and measurement is the act that makes one option stand out. Like moonlight on water, many ripples, one sparkle. Now, to describe this world properly, physicists needed a new kind of language. Not the language of definite paths, but the language of evolving possibility. That language arrived in the form of an equation that is often spoken about with a kind of reverence, not because it is mystical, but because it works with astonishing consistency. Schrödinger's equation. And I promise, we will not turn this into a mathematics lesson. We will not do symbols on a chalkboard. We will treat it like a story about how possibility flows. In quantum mechanics, a particle is not always described as a dot with a precise position and speed. Instead, it is described by something called a wave function. A wave function is not a physical wave in the ordinary sense, like water or sound, but it behaves similarly in that it can spread, interfere, and form patterns. Most importantly, the wave function tells us the probability of finding the particle in different places, in different states, if we decide to measure it. It is like a soft map of likelihood. Not a statement of it is here. More like it could be here and also there, and here is how strongly those possibilities weigh. Schrödinger's equation describes how that wave function changes over time, how the map of likelihood gently shifts and ripples as the system evolves. And when a measurement occurs, the wave function seems to collapse into a definite outcome. Again, you do not need to fight with that word collapse. You can hold it as an image, a fog that suddenly reveals one clear point when a light shines through it, or a chord that resolves into a single note when you place your ear close enough to listen. This wave-based description explains a great deal. It explains why electrons in atoms do not behave like tiny planets spiraling into a nucleus. Instead, they form stable patterns, standing waves of probability around the nucleus, which we often picture as soft clouds, orbitals. Those clouds are not just diagrams. They reflect real statistical patterns measured in experiments. A calm reminder that the deep structure of matter is not built from little marbles, but from shaped possibilities. And now we reach another quiet cornerstone. A principle that sounds at first like a limitation of human measurement, but is deeper than that. The uncertainty principle. In the everyday world, you can know where something is and how fast it is moving, to excellent precision. But at the quantum scale, there is a trade-off. The more precisely you know a particle's position, the less precisely you can know its momentum, and the more precisely you know momentum, the less precisely you can know position. This is not just about clumsy tools. It is built into the wave nature of quantum systems. A narrow, sharply localized wave implies a wide range of momenta. A smooth wave with a well-defined momentum implies a spread-out position. You can picture it like this. If you try to pinch a wave into a tight spot, it becomes more jagged, more mixed, less clear in its rhythm. If you let it be smooth and rhythmic, it spreads across space. That trade-off is not a flaw. It is part of why atoms are stable, part of why chemistry is possible, part of why matter holds its shape without collapsing into a dense, silent heap. And it is also, in a gentle way, a reminder. Some forms of certainty are not available, not because we are not clever enough, but because nature itself does not contain that certainty to be harvested. If that feels philosophical, it can be. But it is also practical, measurable, and deeply woven into how the world behaves at its smallest scales. Now, as your attention drifts, it may be helpful to pause and gently recap, not as revision, but as a soft settling. We began with warm objects glowing, a problem in the mathematics, Planck proposing tiny packets of energy, Einstein proposing that light itself can arrive as packets, photons, the double-slit experiment showing wave-like patterns even when photons arrive one at a time, and the pattern changing when path information is measured. Schrödinger's equation describing how the wave of possibility evolves, and Heisenberg's uncertainty principle describing a fundamental trade-off in what can be known simultaneously. And as we move onward, we will meet two more famous ideas, ones that sound like they belong in a dream: superposition and entanglement. Superposition is one of the ideas that gives quantum physics its reputation for strangeness, but at its core, it is a direct consequence of the wave-based description of matter. When a system is described by a wave function, it is not limited to a single outcome. Instead, multiple possible states can exist together within that description. In everyday terms, an object tends to have a clear property at any given moment. A switch is either on or off. A coin rests heads or tails. These categories feel absolute because, at human scales, uncertainty is vanishingly small. But at quantum scales, the wave function naturally includes several possibilities at once. An electron, for example, can exist in a superposition of positions. Its wave function may assign a certain likelihood to being found in one region of space, and a different likelihood to another. Until a measurement is made, the theory does not say the electron is secretly in one place and merely hidden from us. Instead, the electron is described as occupying all allowed possibilities simultaneously, weighted by probability. This is not philosophical decoration. It is a practical statement about how quantum systems behave in experiments. Superposition is visible in interference patterns, in atomic energy levels, and in the way particles respond to fields. It is a mathematical fact that has been confirmed repeatedly, not an optional interpretation. One way to picture superposition is to imagine a musical chord. A chord is not a single note played quickly one after another. It is several notes existing together at the same time. Only when you isolate one string or one tone does a single note emerge. In a similar way, a quantum system can contain several allowed states at once, until interaction or measurement selects one outcome. This principle becomes especially clear when studying particles with a property called spin. Spin is not literal rotation, but an intrinsic quantum property that behaves in some ways like angular momentum. For certain particles, spin can be measured along a chosen direction, and the result will be one of two possible values. Before measurement, the particle can exist in a superposition of both spin states. After measurement, only one value remains. The shift from superposition to a single outcome is often referred to as collapse of the wave function. The term can sound dramatic, but it simply reflects a change in description. Before measurement, the system is described by a spread of probabilities. After measurement, the description updates to reflect the observed result. This transition raises an important question. What exactly counts as a measurement? In classical physics, measurement is passive. A thermometer reads temperature. A ruler reads length. The object being measured is assumed to have those properties regardless of whether anyone looks. In quantum physics, measurement is an interaction. It involves exchange of energy or information between systems. That interaction alters the system being measured in a fundamental way. This is why superposition is difficult to maintain. Quantum systems are extremely sensitive to their environment. Contact with stray photons, air molecules, or surrounding fields can act as a measurement. These interactions entangle the system with its surroundings and effectively destroy the clean superposition. This process is known as decoherence. Decoherence does not require consciousness or observation in any human sense. It is a physical process. When a quantum system becomes strongly linked to many environmental degrees of freedom, its wave function no longer behaves like a coherent whole. The system begins to behave classically, with definite outcomes replacing interference. This explains why quantum superposition is rarely observed in large objects. A dust particle, a grain of sand, or a living organism interacts with its environment constantly. Those interactions rapidly eliminate coherent superpositions. As atomic and subatomic scales, however, isolation is possible, and superposition becomes observable. This brings us to one of the most famous illustrations in the history of physics: Schrödinger's cat. The thought experiment was proposed not as a claim, but as a critique. Erwin Schrödinger wanted to highlight what he saw as an unresolved tension in quantum mechanics. If the theory allows superpositions at small scales, and if measurement causes collapse, where exactly does the transition occur? The scenario is deliberately extreme. A sealed box contains a radioactive atom, a detector, a mechanism, and a cat. If the atom decays, the detector triggers the mechanism, and the cat dies. If it does not decay, the cat remains alive. According to quantum theory, before observation, the atom exists in a superposition of decayed and not decayed states. If the system is treated purely quantum mechanically, the entire contents of the box become entangled. The atom, detector, mechanism, and cat are described by a combined wave function. In that description, the cat is neither simply alive nor simply dead. It is part of a superposition correlated with the atomic state. Schrödinger found this conclusion unacceptable. His point was not that cats truly exist in such states, but that quantum mechanics lacks a clear rule for when superposition ends and classical reality begins. The thought experiment exposes a boundary problem rather than proposing a physical situation to be tested. Different interpretations of quantum mechanics respond to this problem in different ways. Some suggest that wave function collapse is a real physical process triggered by measurement. Others propose that collapse is not real at all, and that all possible outcomes continue to exist in separate branches. Still others treat the wave function as a tool for calculating probabilities, not as a literal description of reality. What matters experimentally is that quantum predictions remain accurate regardless of interpretation. The mathematics works. The disagreement lies in what the mathematics means. As quantum research progressed, another phenomenon emerged that deepened the mystery while also providing powerful tools: quantum entanglement. Entanglement occurs when two or more particles are described by a single shared wave function. In such cases, the properties of the particles cannot be described independently, even when the particles are separated by large distances. A useful comparison involves pairs of properties rather than objects. If two particles are entangled in spin, for example, measuring the spin of one immediately determines the spin of the other. This is not because information travels between them, but because their properties were never independent to begin with. Before measurement, neither particle has a definite individual state. The system as a whole has a definite relationship. Measurement reveals that relationship in a specific way. Albert Einstein famously objected to this idea, referring to it as spooky action at a distance. His concern was that entanglement seemed to violate the principle that nothing can influence something else faster than light. To him, this suggested that quantum mechanics was incomplete. In response to this concern, physicist John Bell developed a way to test whether hidden variables could explain entanglement. Bell derived inequalities that must be satisfied if local hidden variables exist. Quantum mechanics predicts violations of those inequalities. Experiments performed over decades have consistently supported the quantum predictions. Entangled particles violate Bell's inequalities, ruling out a large class of classical explanations. The correlations observed cannot be explained by pre-existing properties assigned at creation. Despite this, entanglement does not allow faster-than-light communication. The outcomes of measurements are random. While the correlations are strong, they cannot be used to send controlled information. Entanglement has moved from philosophical curiosity to practical resource. It is used in quantum cryptography, where it provides security guaranteed by physical laws. It plays a central role in quantum computing, enabling coordinated operations across many quantum bits. It is also studied in fundamental research, exploring the structure of space and time. Some modern theories suggest that entanglement may underlie the geometry of spacetime itself. In these views, space is not a background in which quantum systems exist, but something that emerges from networks of entangled relationships. This idea remains speculative, but it reflects how central entanglement has become in theoretical physics. At this stage, quantum mechanics presents a consistent picture. Systems are described by wave functions. Those wave functions evolve according to precise equations. Measurements produce definite outcomes with predictable probabilities. Superposition and entanglement are not anomalies, but essential features. What remains unsettled is interpretation. Quantum mechanics does not tell us what reality is in a simple classical sense. It tells us how outcomes relate to preparation and measurement. Whether the wave function represents physical reality, information, or something else entirely remains an open question. As research continues, physicists explore ways to unify quantum mechanics with gravity, to understand how spacetime behaves at the smallest scales, and to determine whether deeper principles underlie the theory. These efforts build on the same foundations introduced over a century ago. Quantum physics, explained slowly, is less about mystery than about precision. It replaces certainty with probability, but it does so in a structured and testable way. The theory does not claim that anything can happen. It specifies exactly what can happen and how likely each outcome is. That balance between openness and constraint is what gives quantum mechanics its power. It describes a universe that is not rigid, but not chaotic. A universe where the smallest elements follow rules that are subtle, mathematical, and remarkably consistent. As the scale increases, those rules fade into the classical patterns we recognize. The solid world emerges from the probabilistic one, not by contradiction, but by accumulation and interaction. The boundary between the two is not sharp, but gradual. Understanding that transition remains one of the central goals of modern physics. To move forward, it helps to adjust one assumption that often hides in everyday language. We often speak as if particles are the fundamental building blocks of reality, with fields acting as secondary features that describe how particles interact. In modern physics, that picture is reversed. In quantum field theory, fields come first. A field is something that exists everywhere in space. Temperature is a familiar example. At every location in a room there is a temperature value, even if it changes gradually from one place to another. A magnetic field assigns a direction and strength to every point in space. You do not need an object at each location for the field to exist. The field is the object. Quantum fields work in a similar way, but they are more fundamental. According to this framework, every type of particle corresponds to its own field. There is an electron field, a photon field, a quark field, and so on. These fields fill all of space, even in regions that appear empty. A particle in this view is not a tiny object traveling through emptiness. It is a localized excitation of a field, a small ripple or vibration that carries energy and momentum. When an electron is detected, what is being observed is a concentrated excitation of the electron field. When a photon is detected, it is an excitation of the electromagnetic field. This shift in perspective resolves several puzzles that arise in particle-based thinking. It explains why particles of the same type are truly identical. Every electron has exactly the same mass, charge, and spin because every electron is an excitation of the same underlying field. There are not many electrons with similar properties. There is one electron field expressing itself in many places. It also explains how particles can be created and destroyed. In nuclear reactions or high-energy collisions, particles appear and disappear. From a field perspective, this is not mysterious. Energy supplied to a field can create excitations. When excitations interact and decay, energy returns to the field or transfers to other fields. This view becomes especially important when discussing the vacuum. In everyday language, a vacuum suggests emptiness, a region with nothing in it. In quantum physics, the vacuum is not empty at all. It is the lowest energy state of all fields. Even when no particles are present, the fields themselves remain. Because quantum fields obey the uncertainty principle, they cannot be perfectly still. A field cannot have both exactly zero energy and perfectly defined properties at the same time. As a result, even in the vacuum state, fields fluctuate. These fluctuations are small, brief, and tightly constrained, but they are real. They are known as vacuum fluctuations. Vacuum fluctuations do not mean that particles are constantly popping in and out of existence in a literal sense, as is sometimes said in popular descriptions. What they mean is that the fields undergo continual, measurable variations around their lowest energy state. These variations can have observable consequences. One such consequence is the Casimir effect. When two uncharged metal plates are placed very close together in a vacuum, they experience a small attractive force. This force arises because the quantum vacuum between the plates allows fewer field modes than the vacuum outside. The difference in allowed fluctuations creates a pressure imbalance that pushes the plates together. This effect has been measured with high precision. It is not a theoretical curiosity. It is a direct demonstration that the vacuum has physical structure. Another consequence appears in atomic energy levels. Vacuum fluctuations interact with electrons bound to atoms, slightly shifting their energy states. These shifts have been observed and measured, and they agree with predictions made using quantum field theory. From this perspective, empty space becomes an active participant in physical processes. It is not a passive backdrop. It is a dynamic system governed by the same quantum rules as matter and radiation. This leads to an important conceptual unification. Particles, forces, and even emptiness are described using the same language of fields and excitations. The distinction between something and nothing becomes less sharp. Quantum field theory also provides the framework for understanding forces. In classical physics, forces act at a distance through fields. In quantum physics, interactions between particles arise from interactions between fields. These interactions can be described as the exchange of excitations. For example, the electromagnetic force between charged particles can be described as arising from interactions with the electromagnetic field. In calculations, this interaction is often represented as the exchange of virtual photons. These are not particles in the same sense as detectable photons. They are mathematical components of the field interaction, constrained by quantum rules. The same framework applies to other forces. The strong force arises from interactions within the quark and gluon fields. The weak force involves interactions mediated by heavy field excitations associated with certain particles. Gravity, in its quantum description, is expected to arise from a gravitational field, though a complete and experimentally confirmed quantum theory of gravity remains unfinished. What unites these ideas is the realization that the universe is structured less like a collection of objects and more like an interconnected system of fields, each influencing the others according to precise rules. Time also plays a subtle role in this framework. In non-relativistic quantum mechanics, time appears as an external parameter. Systems evolve in time, but time itself is not treated as an operator in the same way position or momentum are. In quantum field theory, time and space are combined into spacetime, following the principles of relativity. This combination introduces constraints on how information and influence can propagate. Interactions respect the speed of light as a limiting factor. Even though entanglement produces correlations that appear instantaneous, no usable signal travels faster than light. The structure of spacetime remains intact. Causality, while more subtle than in classical physics, is preserved. Effects do not precede causes in any operational sense. Quantum mechanics allows uncertainty and probability, but it does not permit arbitrary violations of temporal order. This balance between flexibility and constraint is a recurring theme. Quantum theory allows systems to exist in superpositions, to become entangled, and to fluctuate even in their lowest energy states. At the same time, it enforces strict mathematical limits on what is possible. As experiments probe smaller distances and higher energies, quantum field theory continues to make accurate predictions. Particle accelerators test these predictions by colliding excitations of fields and observing the resulting patterns. Each successful prediction strengthens confidence in the underlying framework. At the same time, unanswered questions remain. One of the most significant involves gravity. Gravity is described extremely well by general relativity, a theory that treats spacetime as a smooth, curved structure shaped by mass and energy. Quantum mechanics, by contrast, treats fields as fluctuating and probabilistic. Combining these two descriptions into a single consistent theory has proven difficult. Several approaches exist. Some attempt to quantize gravity directly, treating spacetime itself as subject to quantum rules. Others propose that spacetime emerges from more fundamental quantum degrees of freedom. These ideas remain under active investigation, and experimental guidance is limited. Despite this, quantum physics already shapes many aspects of modern technology. Semiconductors rely on quantum behavior of electrons in solids. Lasers depend on stimulated emission, a quantum process. Magnetic resonance imaging exploits quantum properties of atomic nuclei. Atomic clocks rely on precise quantum transitions to keep time with extraordinary accuracy. These applications work not because quantum physics is mysterious, but because it is reliable. Once the rules are understood, they can be applied with confidence. At this point in the story, quantum physics appears less like a collection of paradoxes and more like a coherent framework. The apparent strangeness often comes from applying classical intuition in regimes where it no longer applies. When the appropriate concepts are used, the behavior becomes consistent, even if it remains unfamiliar. The challenge moving forward is not whether quantum mechanics works, but how it fits into a broader picture of reality. Questions about the origin of spacetime, the nature of measurement, and the role of information continue to guide research. What has emerged so far is a view of the universe in which stability arises from fluctuation, structure arises from fields, and certainty arises only in limits where probabilities narrow sharply. The solid world is not separate from the quantum one. It is built from it. And as this framework extends outward, from particles to fields, from fields to spacetime, and from spacetime to the early universe, the same principles continue to apply. Probability, interaction, and constraint remain central. Quantum physics, when explained slowly, becomes less about surprise and more about continuity. It shows how complex, reliable structures can emerge from simple, well-defined rules operating at scales far removed from everyday experience. That continuity is what allows the theory to connect the smallest measurable processes to the largest questions in cosmology. One of the quieter shifts introduced by quantum physics is a change in how measurement itself is understood. In classical theories, measurement is assumed to reveal a property that already exists. The object is thought to possess a definite position, energy, or momentum, whether or not anyone looks. In quantum mechanics, measurement is not merely a passive reading. It is an interaction between systems, one of which is used as a measuring device. This interaction creates correlations that did not exist before. What is observed is not simply uncovered, it is produced through the interaction. This does not mean that reality depends on human awareness. It means that physical systems influence one another in ways that restrict which outcomes can occur. A measurement device is just another physical system, governed by the same rules as the particle it measures. From this perspective, measurement can be understood as an exchange of information. When two systems interact, information about certain properties becomes shared between them. That shared information defines the result. This approach helps clarify why quantum mechanics speaks in probabilities. Before interaction, the system allows several outcomes. After interaction, only one outcome remains compatible with the information exchanged. Information in quantum mechanics behaves differently from information in classical systems. It cannot always be copied. It cannot always be separated from the system that carries it. These limitations are not practical inconveniences. They are fundamental rules. One example is the no cloning principle. It states that it is impossible to create an exact copy of an unknown quantum state. This is not a technological limitation. It follows directly from the linear structure of quantum theory. Attempting to duplicate a quantum state inevitably disturbs it. This principle has important consequences. It explains why quantum communication can be made secure. Any attempt to intercept or copy a quantum signal leaves detectable traces. It also shapes the way quantum computers process information, forcing designs that rely on entanglement rather than duplication. Information also plays a role in understanding time. At a microscopic level, the fundamental equations of quantum mechanics are largely time-symmetric. If a process is allowed to occur forward in time, the equations often allow it to occur backward as well. This symmetry contrasts with everyday experience, where time has a clear direction. In daily life, causes come before effects. Objects age. Systems evolve toward disorder. This directionality is known as the arrow of time, and it is closely related to entropy. Entropy measures the number of ways a system can be arranged internally while appearing the same from the outside. A system with low entropy has few possible arrangements. A system with high entropy has many. As systems evolve, they tend to move from low entropy states to high entropy states. This is not because individual particles prefer disorder, but because high entropy arrangements are overwhelmingly more numerous. Quantum mechanics does not remove this tendency. Instead, it provides the microscopic foundation for it. When quantum systems interact and become entangled with their environment, information about their precise states spreads into many degrees of freedom. Reversing that process would require collecting and coordinating vast amounts of information, which becomes practically impossible. This spreading of information is another way to describe decoherence. It marks the transition from quantum behavior, where interference is visible, to classical behavior, where definite outcomes dominate. Time, in this view, is not something that flows independently of physical processes. It is a measure of change, tied to how information is distributed and how correlations evolve. The arrow of time emerges from the accumulation of entanglement and a growth of entropy. At very small scales and over very short intervals, quantum processes do not privilege a direction of time. At larger scales, where many interactions occur, a direction becomes apparent. This understanding helps bridge the gap between quantum mechanics and thermodynamics. It shows how irreversible behavior can arise from reversible laws. The relationship between time and quantum mechanics becomes even more intriguing when considering gravity. In general relativity, time is woven together with space into a dynamic geometry. The presence of mass and energy affects how time flows relative to different observers. Clocks tick at different rates depending on motion and gravitational fields. Quantum mechanics, in contrast, treats time as a background parameter. Reconciling these views is one of the central challenges of theoretical physics. Some approaches suggest that time itself may be an emergent property. Rather than being fundamental, it may arise from correlations between quantum systems. In such models, time is defined by change within the universe, not imposed from outside. This idea remains speculative, but it reflects a broader trend. Concepts once treated as basic, such as particles, space, and even time, are increasingly seen as arising from deeper structures. These questions become unavoidable when turning attention to the early universe. According to modern cosmology, the universe began in a state of extremely high density and temperature. Quantum effects would have been significant. Fields fluctuated strongly. Space-time itself may have been subject to quantum uncertainty. During this early period, small quantum fluctuations were stretched by cosmic expansion. Over time, these fluctuations became the seeds of large-scale structure. Galaxies, clusters, and cosmic voids trace their origins to tiny variations in quantum fields. This connection has been tested through observations of the cosmic microwave background, a faint glow that fills the universe. The patterns observed in this radiation match predictions based on quantum fluctuations amplified during cosmic inflation. In this way, quantum mechanics reaches far beyond the laboratory. It influences the distribution of matter across billions of light-years. The same principles that govern electrons in atoms also shape the structure of the universe. As the universe expanded and cooled, quantum processes gradually gave way to classical behavior. Fields settled into stable configurations. Particles formed. Atoms combined. Stars ignited. The transition from quantum to classical did not happen at a single moment. It occurred gradually through interaction, entanglement, and decoherence. Even today, quantum processes continue beneath the surface of everyday phenomena. This layered view of reality helps explain why quantum mechanics can feel both strange and familiar. It governs the foundations of matter, but its effects are often averaged out at larger scales. Understanding this layering is essential for interpreting quantum physics without unnecessary mysticism. The theory does not claim that reality is arbitrary or unknowable. It provides a precise framework for predicting outcomes where classical descriptions fail. As research continues, physicists explore how quantum information, space-time geometry, and gravity might fit into a unified picture. These efforts are ongoing, and many ideas remain provisional. What is already clear is that quantum physics is not a collection of isolated puzzles. It is a coherent structure that connects energy, matter, information, and time. By examining these connections slowly, the theory becomes less intimidating. Each concept builds on the previous one. Fields lead to particles. Interactions lead to entanglement. Entanglement leads to decoherence. Decoherence leads to classical behavior. The world that feels solid and continuous emerges from this chain, not in spite of quantum mechanics, but because of it. One of the remaining challenges in quantum physics lies in understanding the limits of measurement itself. Even with precise instruments and careful preparation, certain quantities resist exact determination. This is not due to experimental imperfection, but to the structure of the theory. When measurements are repeated many times under identical conditions, quantum mechanics does not predict a single outcome. It predicts a distribution. The role of theory is not to specify which result will occur in an individual trial, but to describe the pattern that emerges across many trials. This statistical nature is not a sign of incompleteness. It is a reflection of how quantum systems are defined. The wave function encodes all that can be known about a system prior to interaction. Asking for more detail than the wave function provides is equivalent to asking a question the theory does not allow. This perspective shifts how explanation works. Instead of tracing exact trajectories, quantum physics explains regularities. It explains why certain outcomes are common and others rare. It explains why averages behave predictably even when individual events do not. A familiar analogy comes from radioactive decay. The exact moment when a single atom decays cannot be predicted. But the decay rate of a large collection of atoms is remarkably stable. This stability arises from probability applied across many systems. The same logic governs quantum processes at all scales. Predictability emerges through repetition and aggregation. Uncertainty at the level of individuals gives way to reliability at the level of ensembles. This statistical structure also places limits on control. While quantum systems can be prepared in specific states, the outcomes of measurements cannot be forced beyond what the probability distribution allows. This constraint underlies many of the challenges in quantum technology. Quantum control requires isolation, precision, and careful management of interactions. Even then, outcomes remain probabilistic. Engineering in this domain involves shaping distributions rather than commanding exact results. Despite these limitations, remarkable progress has been made. Experiments now routinely manipulate individual atoms, ions, and photons. Quantum states can be prepared, entangled, and measured with high fidelity. These achievements demonstrate not only the correctness of quantum theory, but its practical power. As techniques improve, attention turns to deeper questions about interpretation. Different interpretations of quantum mechanics agree on predictions, but differ in their descriptions of what is fundamentally real. Some interpretations treat the wave function as a real physical object. In these views, the wave function exists independently of observation, and measurement reveals a particular branch of that reality. Other interpretations treat the wave function as a tool for organizing knowledge. In this view, quantum mechanics does not describe reality directly, but rather our expectations about outcomes given specific preparations. There are also interpretations that modify the theory itself, introducing additional mechanisms to explain collapse or limit superposition. These proposals are carefully constrained by experimental evidence and remain topics of active research. What unites these approaches is that none alter the practical success of quantum mechanics. The predictions remain the same. The differences lie in how the mathematical structure is connected to metaphysical claims. This separation between calculation and interpretation is unusual in physics. Most successful theories also offer a clear picture of what exists. Quantum mechanics offers precision without consensus on meaning. For many physicists, this is not a problem. The theory does what it needs to do. It predicts results with unmatched accuracy. It enables technologies that would be impossible otherwise. For others, the lack of a single clear interpretation is an invitation. It suggests that deeper principles may remain undiscovered. This tension has persisted since the early days of the theory. Debates between leading physicists revealed differing intuitions about what science should provide. Some sought completeness and determinism. Others accepted probability as fundamental. Over time, experimental success shifted the focus toward application. Quantum mechanics became a working language rather than a philosophical battleground. Disagreements continued, but quietly. As quantum ideas spread into other fields, new connections emerged. Chemistry, for example, is deeply rooted in quantum principles. The structure of molecules, the nature of chemical bonds, and the behavior of materials all depend on quantum interactions. In solids, electrons occupy energy bands rather than discrete atomic states. These bands determine whether a material behaves as a conductor, an insulator, or a semiconductor. Small changes in structure can produce dramatic changes in behavior. This sensitivity underlies modern electronics. Transistors rely on quantum tunneling and band structure. Light-emitting devices rely on controlled quantum transitions. Sensors exploit quantum coherence to achieve high precision. In biology, quantum effects appear in subtler ways. Certain processes in photosynthesis, for example, show evidence of quantum coherence assisting energy transfer. These effects operate at the edge of decoherence, where quantum and classical behavior overlap. Such findings do not suggest that life is governed by exotic quantum laws. Rather, They show that evolution has taken advantage of physical principles wherever they offer efficiency. As research expands, quantum ideas increasingly intersect with information theory. Concepts such as entropy, encoding, and correlation become central. In this context, physical systems are viewed as carriers and processors of information. This shift reframes familiar questions. Instead of asking what a particle is, one might ask what information it carries. Instead of asking where a system is, one might ask how it is correlated with others. These questions are not abstract. They guide experimental design and theoretical development. They shape how data is interpreted and how limits are understood. One consequence of this information-centered view is a renewed focus on the observer. Not as a conscious agent, but as a physical system that becomes correlated with what it measures. Observation is redefined as interaction. This avoids unnecessary mystery. The observer is not special. Any sufficiently complex system can play the role of a measuring device. The outcome arises from physical correlation, not awareness. This view aligns well with decoherence theory. As systems interact, information spreads. Certain correlations become robust. Others fade. The classical world emerges as a stable pattern within this network of interactions. From this standpoint, the quantum to classical transition is not abrupt. It is gradual and scale-dependent. At small scales and short times, quantum effects dominate. At large scales and long times, classical behavior prevails. Between these regimes lies a rich landscape. Mesoscopic systems, neither fully quantum nor fully classical, exhibit hybrid behavior. Studying these systems helps clarify how emergence works. Emergence is a key concept. It describes how simple rules give rise to complex behavior when applied repeatedly. In quantum physics, emergence explains how deterministic equations yield probabilistic outcomes, and how probabilistic rules yield stable structures. This layered understanding reduces the sense of contradiction. Quantum mechanics does not replace classical physics. It underlies it. Classical laws emerge as approximations valid under specific conditions. Recognizing this helps integrate quantum ideas into a broader scientific picture. It shows continuity rather than disruption. Each level of description has its domain of applicability. As attention moves toward the largest scales, quantum principles continue to play a role. The early universe, black holes, and extreme gravitational environments all push theories to their limits. Black holes, in particular, highlight unresolved tensions. They combine strong gravity with quantum effects. Questions about information loss, entropy, and horizon behavior remain open. One well-established result is that black holes possess entropy and temperature. They emit radiation due to quantum effects near the horizon. Over long times, they can lose mass. This realization connects thermodynamics, quantum theory, and gravity in unexpected ways. It suggests that information is not destroyed, but its fate is subtle. These insights have reshaped how physicists think about space, time, and information. They hint that space-time itself may have a microscopic structure governed by quantum rules. Whether this structure takes the form of discrete elements, networks of entanglement, or something else entirely remains unknown. What is clear is that quantum mechanics continues to guide inquiry even where it is incomplete. Throughout its development, quantum physics has shown a consistent pattern. Each time it has seemed conceptually troubling, it has proven experimentally reliable. Each time it has challenged intuition, it has delivered precise results. This reliability is the foundation of trust in the theory. It allows physicists to explore boldly while remaining grounded in evidence. As the story continues, the emphasis shifts from foundational questions to synthesis. How do all these pieces fit together? How does information flow shape reality? How does structure arise from fluctuation? These questions do not demand immediate answers. They define a direction rather than a destination. As quantum physics has matured, one of its most productive shifts has been a move away from asking what things are and toward asking how systems relate. This relational view does not deny the existence of physical objects, but it emphasizes interactions, correlations, and shared structure over isolated properties. In this view, a quantum state is not an intrinsic label attached to a particle. It is a description of how that system is related to others, including measuring devices, environments, and reference frames. What can be said about a system depends on how it is connected. This perspective helps explain why different observers can describe the same system in different ways without contradiction. If two observers interact with a system under different conditions, they may legitimately assign different quantum states. These descriptions are not competing truths. They reflect different relational contexts. Such ideas have led to the development of relational interpretations of quantum mechanics. These approaches treat states as relative, not absolute. There is no single universal wave function that all observers must agree on in detail. Instead, there are consistent networks of descriptions tied together by interaction. This does not weaken the predictive power of the theory. When observers compare notes through interaction, their descriptions align. Agreement emerges through correlation, not assumption. Relational thinking also clarifies long-standing puzzles about measurement. A measurement outcome is not a sudden creation of reality, but the establishment of a stable correlation between systems. Once that correlation exists, it can be shared, amplified, and recorded. Amplification is crucial. In practice, a measurement is not a single microscopic interaction. It is a cascade. A quantum event triggers a chain of interactions that spreads information across many degrees of freedom. This process makes outcomes robust. A detector click, a photographic mark, or a digital signal represents the end of a long chain of correlations. At that point, reversing the process would require undoing interactions across vast numbers of particles. This is why outcomes appear definite. The apparent collapse of the wave function can be understood as a shift in description once correlations become effectively irreversible. The underlying quantum evolution continues, but certain alternatives become inaccessible. This framing removes the need for special rules tied to observation. Measurement is not an exception. It is an ordinary physical process that becomes distinctive through scale. As this understanding developed, attention increasingly turned toward quantum information as a unifying concept. Information is not treated as abstract bookkeeping, but as a physical quantity tied to states, correlations, and transformations. This idea was famously captured in the phrase, "Information is physical." It reflects the insight that storing, transmitting, and erasing information all have physical consequences governed by quantum laws. One example is Landau's principle, which links information erasure to energy dissipation. Erasing a bit of information requires a minimum amount of energy to be released as heat. This principle connects thermodynamics, computation, and quantum mechanics. At quantum scales, the relationship becomes richer. Information is encoded in quantum states. transformations correspond to physical operations. Limits on copying and measurement impose fundamental constraints on processing. Quantum computing exploits these constraints rather than fighting them. Instead of copying states, quantum algorithms use superposition and entanglement to explore many possibilities in parallel. Measurement then extracts specific information from the resulting state. This does not mean that quantum computers try every answer at once in a literal sense. Rather, they manipulate probability amplitudes so that unwanted outcomes cancel and desired outcomes reinforce. The final measurement reveals a result that reflects this structured interference. The success of this approach depends on maintaining coherence across many components. Decoherence, which spreads information into the environment, is the primary obstacle. Engineering around it requires isolation, error correction, and careful control. Quantum error correction introduces another subtle insight. While individual quantum states cannot be copied, information encoded across entangled systems can be protected. Errors affecting one part can be detected and corrected using correlations without measuring the protected information directly. This possibility was once thought impossible. It demonstrates that quantum mechanics allows robustness through structure, even while forbidding duplication. These developments have reshaped how physicists think about complexity. Rather than viewing quantum behavior as fragile and exotic, it is increasingly seen as a resource that can be managed and exploited. As quantum information theory expanded, it began to influence foundational physics. Concepts such as entropy, entanglement, and information flow became central to discussions of space-time and gravity. One striking idea is that the geometry of space-time may be related to patterns of entanglement. In certain theoretical models, distances emerge from the strength of correlations. Regions that are strongly entangled behave as if they are close. Regions with weak entanglement behave as if they are far apart. This does not mean that space is literally made of entanglement in a simple sense. It means that the structure of space-time may depend on underlying quantum relationships. Geometry becomes a derived concept rather than a primitive one. Evidence for this idea comes from studies of black holes and holographic models of gravity. In these models, information encoded on a boundary can describe a higher dimensional interior. Entanglement plays a central role in maintaining this correspondence. These ideas remain theoretical, but they offer a glimpse of how quantum mechanics might eventually be reconciled with gravity. They suggest that spacetime itself could be an emergent phenomenon, arising from deeper quantum structure. Emergence appears again and again in this story. Simple rules give rise to complex behavior. Local interactions produce global patterns. Probabilistic laws yield stable outcomes. This pattern mirrors developments in other sciences. In biology, complex organisms emerge from simple biochemical interactions. In economics, markets arise from individual choices. In physics, classical reality emerges from quantum rules. Recognizing this continuity helps reduce the sense that quantum mechanics is an alien intrusion into science. It is another layer in a hierarchy of descriptions, each appropriate to a particular scale. At human scales, classical mechanics works extremely well. At atomic scales, quantum mechanics becomes essential. At cosmological scales, relativity dominates. Where these regimes overlap, careful synthesis is required. This layered view also guides how theories are tested. Predictions must be matched to the scale at which they apply. Discrepancies often signal that a different description is needed, not that reality is inconsistent. Throughout its history, quantum physics has advanced by refining its language. Concepts that once seemed paradoxical become familiar with use. What initially feels strange often becomes routine once its domain is understood. Wave-particle duality, superposition, and entanglement are now standard tools rather than philosophical provocations. They are taught, measured, and applied. This normalization does not remove mystery entirely. It relocates it. Instead of asking how something can be both a wave and a particle, one asks how fields behave under certain conditions. Instead of asking whether reality exists when unobserved, one asks how correlations form and persist. These shifts reflect maturity. The theory no longer needs to shock to justify itself. Its strength lies in coherence and reach. As the picture broadens, it becomes clear that quantum physics is not a closed chapter. It continues to evolve. New experiments probe ever finer details. New technologies demand deeper understanding. New questions arise at the boundaries. Yet the core structure remains remarkably stable. The same principles discovered in the early 20th century continue to organize knowledge today. Their implications continue to unfold. In this sense, quantum physics explained slowly is not a single explanation, but an ongoing process. It is a way of approaching nature that values precision, humility, and openness to revision. Each layer builds on the last. Each insight narrows uncertainty without eliminating it. The result is not a final picture, but a reliable framework within which exploration continues. And as this framework extends further, it begins to encompass not only matter and energy, but information, structure, and the conditions under which knowledge itself becomes possible. As quantum physics continues to extend outward, it increasingly reshapes how limits are understood. In classical thinking, limits often arise from practical constraints, limited precision, limited resources, or limited access. In quantum theory, many limits are structural. They arise from the way physical laws are organized. One such limit concerns how precisely systems can be prepared. While quantum states can be engineered with remarkable accuracy, no preparation can escape uncertainty entirely. Every state occupies a region in a space of possibilities. Narrowing one feature necessarily broadens another. This is not a flaw in technique. It is a consequence of how states are defined. Precision has a cost, and that cost appears in complementary variables. As a result, control in quantum systems is always a balance rather than an absolute. Another limit concerns predictability. Even with perfect knowledge of a quantum state, outcomes remain probabilistic. This unpredictability is not ignorance. It is built into the formalism. Quantum mechanics does not describe hidden trajectories that could, in principle, be revealed. It describes distributions that cannot be reduced further. This distinction matters. In classical chaos, systems are unpredictable because small differences in initial conditions grow rapidly. In quantum mechanics, unpredictability persists even when the state is known exactly. The randomness is irreducible. This has led to the use of quantum systems as sources of genuine randomness. Quantum random number generators exploit the inherent unpredictability of measurement outcomes. Unlike classical algorithms, these sources do not rely on complexity or secrecy. They rely on fundamental physical processes. Randomness, once viewed as a nuisance, becomes a resource. Limits also appear in how information can be transmitted. Quantum correlations can be strong, but they cannot be used to send signals faster than light. This preserves causality while allowing non-classical correlations. The balance between correlation and communication reflects a deeper structure. Nature permits coordination without control. Systems can be linked without allowing influence to propagate arbitrarily. This constraint maintains consistency across space-time. As these ideas developed, attention turned toward how classical behavior emerges so reliably from quantum rules. Everyday objects follow predictable paths. Measurements yield stable results. The world appears definite. The explanation lies not in abandoning quantum mechanics, but in understanding how it scales. Large systems interact constantly with their environments. Each interaction spreads information outward. Over time, quantum coherence becomes distributed across many degrees of freedom. Interference effects wash out. What remains are robust patterns. These patterns correspond to classical states. They are not perfectly sharp, but they are stable enough to persist. Once established, they reinforce themselves through feedback with the environment. This process explains why certain variables become classical. Position, for example, tends to become well-defined because interactions with surroundings continually monitor it. Other variables, such as phase, are more easily disrupted and fade quickly. The environment acts as a witness. It records information redundantly. Many fragments of the environment carry the same information about the system. This redundancy allows multiple observers to agree without disturbing the system further. This idea has been formalized in approaches that study how information spreads and stabilizes. These studies show that classical reality is not imposed. It emerges as the most stable solution under continuous interaction. The implication is subtle but important. Classical facts are not primary. They are selected. This selection does not require intention or awareness. It arises from dynamics. States that leave clear, persistent records survive. States that do not are suppressed. Seen this way, the quantum to classical transition resembles natural selection. Variants compete under environmental constraints. Stable patterns dominate. Fragile ones disappear. This analogy is not exact, but it captures the logic. Stability determines visibility. As understanding deepened, researchers began applying similar ideas to spacetime itself. If classical space emerges from quantum rules, then geometry may also be subject to selection. In some theoretical models, spacetime properties arise from patterns of entanglement that are stable under interaction. Geometry becomes a summary of relationships rather than a fixed stage. This line of thinking has influenced approaches to quantum gravity. Rather than quantizing spacetime directly, some theories seek to derive it from more fundamental elements. These elements may not resemble space or time at all. They may be abstract structures whose relationships produce familiar dimensions at large scales. Such ideas remain speculative, but they are guided by consistency. Any successful theory must reproduce known results while extending them smoothly. The challenge is severe. Quantum mechanics and general relativity are both extraordinarily successful, yet they are built on different assumptions. One emphasizes probability and superposition. The other emphasizes geometry and continuity. Bridging this gap requires care. Simple combinations fail. New concepts are needed. Despite this difficulty, progress continues. Mathematical frameworks evolve. Experimental techniques improve. Indirect tests probe regimes where quantum gravity effects might appear. Even without a complete theory, partial insights accumulate. Black hole thermodynamics, holographic principles, and entanglement entropy all suggest deep connections between information and geometry. These connections reinforce a recurring theme. Information is not merely descriptive. It plays an active role in physical law. This role reshapes how questions are framed. Instead of asking where something is, one might ask how information about it is distributed. Instead of asking what exists, one might ask what correlations are stable. This shift does not eliminate realism. It refines it. Reality becomes relational and structured rather than point-like. As the framework expands, the language of quantum physics grows more unified. Concepts once confined to laboratories now inform cosmology. Ideas developed to explain atoms now shape theories of space-time. This unification does not mean simplification. The theory remains mathematically rich and conceptually demanding, but it becomes coherent across scales. The result is a picture in which certainty is contextual. Laws are precise, but outcomes depend on conditions. Stability emerges through interaction. Quantum physics, approached slowly, reveals a universe that is neither rigid nor arbitrary. It is constrained, relational, and layered. At each level, new patterns appear. Atoms form molecules. Molecules form materials. Materials form structures. Structures support life. Life supports knowledge. The foundations of this hierarchy rest on quantum rules. Not because those rules dictate every detail, but because they allow the emergence of complexity. Understanding this hierarchy does not require mastering every equation. It requires recognizing how principles repeat across scales. Probability leads to structure. Interaction leads to correlation. Correlation leads to stability. And stability, in turn, creates the conditions for explanation. As inquiry continues, these principles guide exploration. They do not promise final answers. They offer a reliable way to ask better questions. That is perhaps the lasting contribution of quantum physics. It replaces certainty with structure and mystery with method. And it does so quietly, through rules that remain consistent even as understanding evolves. As the framework widens further, quantum physics begins to influence how limits of knowledge are interpreted. In classical science, uncertainty often reflects incomplete information. With better instruments or better models, it can be reduced. In quantum physics, some uncertainty is fundamental. It does not shrink with improved technique. This distinction reshapes what explanation means. To explain a quantum process is not to eliminate uncertainty, but to describe its structure. The goal is not to predict exact outcomes, but to predict distributions reliably. This approach has proven remarkably successful. Quantum theory provides some of the most accurate predictions ever tested. Calculations of atomic spectra, magnetic moments, and scattering probabilities agree with experiment to extraordinary precision. Such accuracy builds confidence in the framework, even as questions about interpretation remain open. One reason quantum mechanics remains reliable is its internal consistency. The same mathematical structure governs widely different phenomena. Whether describing electrons in atoms, photons in cavities, or fluctuations in the early universe, the same principles apply. This consistency allows techniques developed in one domain to be transferred to others. Methods from condensed matter physics inform cosmology. Ideas from information theory inform gravity. Insights flow across traditional boundaries. Condensed matter systems, in particular, have become a testing ground for quantum ideas. In these systems, large numbers of particles interact under controlled conditions. Collective behavior emerges that cannot be reduced to individual components. Examples include superconductivity, superfluidity, and topological phases of matter. These phenomena arise from quantum coherence, acting across many particles simultaneously. They reveal how quantum rules scale upward. Superconductivity, for instance, occurs when electrons form correlated pairs that move through a material without resistance. This pairing emerges from interaction with the lattice structure of the material. It is a cooperative effect, not a property of isolated electrons. Topological materials exhibit properties that depend not on local details, but on global structure. Certain features remain stable even when the material is disturbed. This robustness arises from underlying quantum constraints. These discoveries have practical implications. They inform the design of new materials, sensors, and devices. They also deepen understanding of how stability can emerge from fragile components. The lesson is consistent. Quantum behavior is not confined to isolated particles. It can organize large systems when conditions allow. This organization relies on symmetry. Symmetries restrict which processes are allowed and which are forbidden. In quantum theory, symmetries are encoded mathematically and lead to conservation laws. When symmetries are exact, they produce strict constraints. When they are broken, new phenomena appear. Symmetry breaking plays a central role in phase transitions, particle physics, and cosmology. In the early universe, symmetries may have been higher. As the universe cooled, symmetries broke, producing distinct forces and particle types. This process is believed to underlie the diversity of matter observed today. Quantum field theory provides the language for describing these transitions. Fields settle into particular configurations, called vacuum states. Different vacuum states correspond to different physical properties. The choice of vacuum is not arbitrary. It depends on conditions and dynamics. Once chosen, it defines the behavior of particles and forces. This idea again highlights emergence. Fundamental equations allow many possibilities. Specific outcomes arise through interaction and constraint. Another domain where quantum ideas reshape understanding is measurement precision. Quantum limits define the ultimate sensitivity of instruments. These limits are not merely obstacles. They can be approached and, in some cases, exploited. Quantum metrology uses entangled states to improve measurement precision beyond classical limits. By correlating components, noise can be reduced and signals amplified. This approach has practical applications in timekeeping, navigation, and sensing. Atomic clocks, for example, use quantum transitions to measure time with extraordinary accuracy. These clocks rely on the stability of quantum states and the predictability of transition frequencies. They define the standard of time used worldwide. Gravitational wave detectors use quantum techniques to reduce noise and enhance sensitivity. By shaping quantum states of light, measurements can approach fundamental limits. These achievements demonstrate that quantum mechanics is not only a theory of the very small, it governs the ultimate performance of large-scale instruments. As technologies advance, the boundary between foundational research and application continues to blur. Questions once considered philosophical now guide engineering decisions. This feedback loop strengthens the theory. Practical success reinforces confidence. Experimental challenges motivate refinement. At the same time, caution remains necessary. Quantum systems are subtle. Intuition developed at classical scales can mislead. Careful analysis is required to avoid overextension. This balance between ambition and restraint characterizes mature science. Quantum physics has reached this stage. It no longer seeks validation through shock. It seeks integration. Integration across scales, across disciplines, and across conceptual frameworks. One area where integration remains incomplete is the relationship between quantum mechanics and consciousness. Some interpretations speculate about connections, but there is no experimental evidence that consciousness plays a special role in quantum processes. Modern approaches treat observers as physical systems. Measurements occur through interaction, not awareness. Consciousness is not required to explain outcomes. This clarification is important. It prevents unnecessary mysticism. It keeps quantum physics grounded in testable principles. Where mystery remains, it is technical rather than metaphysical. How exactly does space-time emerge? How is gravity quantized? What are the ultimate limits of computation and information? These questions are active areas of research. They motivate experiments and theories without undermining established results. As understanding deepens, quantum physics increasingly appears as a framework for constraints. It tells us not only what can happen, but what cannot. Certain transformations are forbidden. Certain states cannot be prepared. Certain measurements cannot be combined. These prohibitions are as informative as allowances. They define the structure of possibility. In this sense, quantum mechanics is less permissive than classical imagination. It does not allow arbitrary behavior. It enforces consistency through mathematical relationships. This enforcement produces order. It shapes how complexity arises and persists. At larger scales, this order becomes the stable world of experience. Objects endure. Patterns repeat. Laws hold. At smaller scales, the same order appears as probability and fluctuation. The difference lies not in contradiction, but in description. Quantum physics provides the description appropriate to the deepest level currently accessible. Classical physics provides the description appropriate to aggregated behavior. Both are valid within their domains. Recognizing this layered validity helps dissolve apparent paradoxes. Theories are not competing truths. They are complementary perspectives. As the account continues, attention naturally turns to the limits of this framework. Where does quantum mechanics itself break down, if at all? What replaces it at extreme scales? These questions do not imply failure. They reflect success. A theory becomes testable at its boundaries, and it is toward those boundaries that the next part of the discussion will move. As inquiry approaches these boundaries, it becomes useful to reflect on how scientific frameworks evolve. No theory arrives complete. Each emerges within a domain of applicability and is refined as that domain expands. Quantum mechanics is no exception. Its core principles have remained stable for more than a century, yet their interpretation and application have continued to develop. This combination of stability and openness is one reason the theory remains productive. At present, quantum mechanics sits at the foundation of known physical law, but it does not stand alone. It coexists with relativity, thermodynamics, and statistical mechanics. Each framework addresses different aspects of reality, and each overlaps with the others in specific regimes. The success of quantum mechanics lies in how smoothly it connects to these neighboring theories. In appropriate limits, quantum predictions reduce to classical ones. Probabilities sharpen. Fluctuations average out. Deterministic behavior emerges. This reduction is not an approximation of convenience. It is a mathematically precise transition. The classical world is not imposed on quantum mechanics. It grows out of it. Understanding this growth clarifies why classical intuition works so well in daily life. The conditions under which quantum effects dominate are narrow. Isolation, low temperature, and small scale are required. Outside these conditions, interactions suppress coherence and enforce classical patterns. This suppression is not absolute. It is statistical. Quantum effects never disappear entirely. They become negligible relative to dominant scales. Even in familiar settings, traces of quantum behavior remain. The stability of matter, the rigidity of solids, and the properties of materials all depend on quantum principles. They are simply encoded in averaged form. This averaging is essential. It allows complex systems to behave predictably. Without it, macroscopic stability would be impossible. At the same time, quantum physics reveals that predictability has limits. No amount of refinement eliminates uncertainty completely. Precision always trades off against other constraints. This recognition shapes how scientific claims are framed. Predictions are accompanied by uncertainty ranges. Confidence is expressed probabilistically. Reliability is defined statistically. These practices are not concessions. They are reflections of how nature behaves. In modern research, this probabilistic mindset extends beyond physics. Fields such as biology, neuroscience, and economics increasingly rely on statistical models. Complex systems resist exact prediction but exhibit stable patterns. Quantum mechanics can be seen as an early example of this broader approach. It formalized the idea that lawfulness does not require determinism. Structure can exist without exact predictability. This idea was controversial when first introduced. It challenged centuries of thinking about causation. Over time, it has become familiar. Familiarity does not mean simplicity. Quantum theory remains mathematically demanding, but its conceptual core has settled into a coherent stance. That stance can be summarized without metaphor. Physical systems are described by states. States encode probabilities. Interactions update states. Measurements reveal outcomes consistent with those probabilities. Nothing in this description requires special observers, hidden intentions, or external influences. It requires only that systems interact according to well-defined rules. These rules are expressed mathematically, because mathematics provides the necessary precision. The language may be abstract, but its consequences are concrete. As the theory has matured, attention has shifted from foundational debate toward synthesis. How do different quantum phenomena fit together? How do they inform a unified picture? One area where synthesis is particularly active is the study of open systems. Most real systems are not isolated. They exchange energy and information with their surroundings. Quantum open system theory describes how states evolve under such conditions. It provides tools for understanding dissipation, noise, and decoherence. These tools are essential for both foundational questions and practical applications. They explain why coherence is fragile and how it can be protected. They clarify how classical behavior emerges from quantum dynamics. Another area of synthesis involves complexity. As systems grow larger, direct calculation becomes infeasible. New methods are needed to identify relevant variables and discard irrelevant detail. Renormalization techniques address this challenge. They show how behavior at one scale depends on parameters at another. Fine details may wash out, leaving only a few controlling factors. This approach has been applied successfully in quantum field theory and condensed matter physics. It explains why diverse systems can exhibit similar behavior near critical points. Such universality reinforces the idea that laws operate at multiple levels. Details matter locally. Patterns matter globally. This layered structure also appears in cosmology. The large-scale structure of the universe reflects early quantum fluctuations, but its evolution follows classical gravitational dynamics. Quantum mechanics sets initial conditions. Classical physics governs subsequent development. The interplay between these regimes is subtle but consistent. It allows cosmology to connect laboratory physics with astronomical observation. As instruments improve, this connection becomes more precise. Measurements of cosmic background radiation, gravitational waves, and particle interactions refine models and constrain possibilities. Each refinement strengthens the framework. Discrepancies are investigated carefully. Some lead to new physics. Others resolve through improved understanding. This iterative process defines scientific progress. Quantum mechanics has endured because it accommodates revision without losing coherence. At times, speculation exceeds evidence. This is unavoidable at the frontiers. The important distinction lies in recognizing what is established and what remains tentative. Established results include the probabilistic structure of measurement, the role of superposition and entanglement, the field-based nature of particles, and the emergence of classical behavior through interaction. Tentative ideas include specific models of quantum gravity, the detailed structure of spacetime at the smallest scales, and the ultimate limits of computation. Maintaining this distinction preserves clarity. It prevents conflating well-tested principles with exploratory hypotheses. As the discussion approaches its later stages, the emphasis naturally shifts from introducing new concepts to revisiting established ones from broader perspectives. Repetition here is not redundancy. It is consolidation. Each pass integrates ideas more deeply. Quantum physics, when explained slowly, benefits from this approach. Concepts that initially seem disconnected reveal underlying unity. Probability, information, interaction, and emergence recur throughout. They link microscopic rules to macroscopic order. The universe described by quantum mechanics is not chaotic. It is constrained, patterned, and surprisingly economical. A small set of principles generates a wide range of phenomena. This economy is a hallmark of successful theory. Whether future discoveries will require modification of these principles remains an open question. History suggests that new theories extend rather than replace old ones. Quantum mechanics itself extended classical physics without rendering it obsolete. Classical laws remain valid where quantum effects average out. A similar extension may occur at the next frontier. Whatever lies beyond quantum mechanics will need to reproduce its successes while addressing its limits. Until then, quantum physics remains the most reliable guide to the structure of reality at its deepest accessible level. It teaches not certainty, but disciplined expectation. Not exact outcomes, but lawful distributions. Not isolated objects, but relational systems. And through these lessons, it offers a framework that is both precise and adaptable, capable of connecting the smallest scales to the largest structures. As the account continues toward its conclusion, the focus will rest increasingly on synthesis rather than novelty, on coherence rather than surprise. The remaining sections will revisit key ideas from slightly different angles, allowing them to settle into a unified picture that reflects both what is known and what remains open. As the narrative draws closer to completion, the emphasis naturally settles on coherence. At this stage, the goal is no longer to introduce unfamiliar ideas, but to allow the existing ones to align into a stable picture. Quantum physics began as a response to specific experimental problems. It was not designed as a philosophical system. Yet over time, it has reshaped how explanation itself is understood. One of its lasting contributions is the recognition that physical description depends on scale. What appears definite at one level may be probabilistic at another. Neither description is privileged. Each applies within a domain defined by interaction and resolution. This insight removes tension between quantum and classical views. They are not rivals. They are layers. At small scales, systems are described by states that encode probabilities. At larger scales, those probabilities concentrate sharply around stable outcomes. The transition is gradual, governed by interaction, averaging, and information flow. The reliability of everyday experience depends on this concentration. Objects persist. Trajectories repeat. Measurements agree. These features emerge not because quantum mechanics fails, but because it succeeds in a regime where alternatives are suppressed. Suppression here does not mean elimination. Quantum effects remain present, but they are distributed across many degrees of freedom. Their influence becomes diffuse. This diffusion explains why classical laws work so well. It also explains why extreme conditions are required to reveal quantum behavior directly. Isolation, low temperature, and precise control reduce diffusion and preserve coherence. Seen in this light, the quantum world is not hidden. It is simply averaged. The same logic applies to uncertainty. At microscopic scales, uncertainty is significant. At macroscopic scales, relative uncertainty becomes negligible. A fluctuation that matters for an electron is irrelevant for a mountain. This scaling property allows physics to remain consistent across domains. It avoids contradiction by recognizing context. Another recurring theme is constraint. Quantum mechanics does not allow arbitrary behavior. It restricts what can be prepared, what can be measured, and how systems can evolve. These restrictions are not limitations of imagination. They are structural features. They define the shape of possibility. By identifying what cannot happen, quantum mechanics clarifies what can. Forbidden transitions sharpen allowed ones. Excluded states define stable configurations. This clarity underlies technological application. Devices work because they operate within allowed regimes. Transistors switch because energy levels are discrete. Lasers emit coherent light because stimulated emission is permitted. Each application relies on constraint rather than freedom. The same principle governs larger structures. Atoms form because certain configurations are stable. Molecules assemble because bonding states minimize energy. Materials acquire properties because collective states are favored. Quantum rules do not dictate outcomes uniquely. They shape landscapes. Systems settle into valleys defined by interaction. Understanding this landscape view helps reconcile probability with order. Outcomes are not random in isolation. They are distributed across structured spaces. This perspective also reframes explanation. To explain a phenomenon, is to describe the structure of its possibility space and the dynamics that guide motion within it. This approach differs from classical narrative, which traces single paths. Quantum explanation traces regions and flows. Once this shift is accepted, many apparent paradoxes dissolve. Wave-particle duality becomes a matter of description rather than contradiction. Measurement becomes interaction rather than revelation. Collapse becomes update rather than event. The theory becomes quieter. It does not shout conclusions. It provides rules and lets patterns emerge. This quietness is part of its endurance. Quantum mechanics has survived intense scrutiny because it does not overclaim. It specifies how to calculate and where calculation applies. Where it does not apply, it remains silent. This restraint is a strength. It leaves room for extension. At the boundaries of the theory, where gravity becomes strong or space-time itself fluctuates, new ideas are required. Yet those ideas must respect what is already known. Any future framework must reproduce quantum predictions in their domain, just as quantum mechanics reproduces classical predictions in its own. This continuity ensures stability of knowledge. Science advances by addition rather than erasure. As the remaining space is filled, repetition becomes intentional. Concepts return in familiar form. Each return integrates them more firmly. Probability, information, interaction, and emergence reappear because they are central. They do not exhaust themselves. Probability does not mean lack of law. It means law expressed statistically. Information does not mean abstraction. It means physical correlation. Interaction does not mean disturbance. It means connection. Emergence does not mean illusion. It means pattern arising from rule. Taken together, these ideas describe a universe that is structured but not rigid, lawful but not deterministic, stable but not static. This description aligns with observation. It supports technology. It guides exploration. Quantum physics does not provide comfort in certainty. It provides reliability through constraint. That reliability is what allows it to underpin so much of modern life without constant attention. Devices function without invoking mystery. Calculations succeed without interpretation. Interpretation remains a human concern. The mathematics does not require it. As understanding deepens, interpretation may converge. Or it may remain plural. Either outcome is compatible with scientific progress. What matters is that predictions remain accurate, limits remain clear, and extensions remain testable. At this stage, the framework is mature. It has absorbed criticism, survived challenge, and adapted to new contexts. Its remaining mysteries are not failures. They are invitations. They indicate where knowledge can grow. The final movement of this account will therefore not seek resolution. It will seek integration. It will revisit the core ideas once more, not to explain them again, but to allow them to rest together as parts of a single structure. From energy packets to fields, from superposition to decoherence, from uncertainty to emergence, the arc remains continuous. Quantum physics, explained slowly, becomes less about strangeness and more about relationship, less about surprise and more about structure, less about answers and more about method. And in that method lies its lasting contribution. At this point, what remains is not the introduction of new mechanisms, but a careful closing of the circle. The pieces are already in place. The task is to show how they coexist without tension. Quantum physics describes a world in which certainty is contextual. Outcomes are definite only within interactions. Properties are stable only when reinforced by their surroundings. This is not a deficiency. It is a description of how complexity sustains itself. The classical world feels solid because it is supported by layers of redundancy. Information about macroscopic objects is copied many times into their environment. Light scatters, air molecules collide, surfaces vibrate. Each interaction carries a trace. Together, these traces lock patterns in place. This is why tables remain tables and planets follow predictable paths. It is not because quantum rules stop applying, but because their effects are spread thinly across enormous numbers of degrees of freedom. Seen this way, classical reality is not imposed from above. It is selected from below. The same principle applies to knowledge. Scientific knowledge stabilizes when results can be reproduced, shared, and embedded in multiple contexts. This mirrors the physical process by which outcomes become classical. Robust patterns survive repeated interaction. Quantum mechanics fits naturally into this view. It does not promise certainty in individual events. It promises structure across many events. Its success lies in consistency, not precision of single outcomes. This approach has reshaped how explanation is evaluated. A good explanation need not trace every detail. It must capture constraints and regularities. It must specify what is possible, what is likely, and what is forbidden. Quantum theory excels at this. It defines boundaries with mathematical clarity. Within those boundaries, behavior unfolds according to probability. This balance between freedom and constraint is what allows creativity in nature. Novel structures arise, but only those consistent with underlying rules persist. From atomic spectra to biological processes, this pattern repeats. Variation appears. Stability selects. Quantum physics does not stand apart from this process. It is its foundation. As the account settles, it becomes clear that many early worries about quantum mechanics arose from misplaced expectations. The theory was never meant to restore classical certainty at small scales. It was meant to replace it with something more general. That replacement succeeded. The unease surrounding probability, superposition, and entanglement reflects a shift in perspective, not a failure of description. Once the shift is made, coherence replaces confusion. What remains unfamiliar becomes simply different. The universe described by quantum physics is not arbitrary. It is governed by symmetry, conservation, and consistency. Its apparent unpredictability is constrained and structured. Even randomness has form. This form is what allows the theory to be used reliably. Engineers do not worry about interpretation when designing devices. They rely on calculation. Those calculations work. This practical success is not accidental. It reflects deep alignment between theory and reality. As research continues, quantum principles continue to guide exploration. New materials, new sensors, and new computational approaches rely on the same rules discovered long ago. At the same time, the theory continues to invite refinement. Questions about space-time, gravity, and information remain open. These questions do not undermine what is known. They extend it. Extension is the natural direction of successful theories. When new frameworks emerge, they will not erase quantum mechanics. they will incorporate it, just as quantum mechanics incorporated classical physics. This continuity ensures that understanding accumulates rather than resets. In this light, quantum physics explained slowly becomes less about explanation and more about orientation. It shows how to think about systems, interactions, and limits. It encourages patience with uncertainty and respect for constraint. It demonstrates that reliability does not require determinism and that structure does not require rigidity. The universe it describes is not chaotic. It is carefully balanced. As the final ideas settle, the emphasis returns to simplicity. A small set of principles generates immense variety. Probability governs detail. Constraint governs form. From these elements, the world unfolds. Atoms bind. Stars shine. Structures form. Observers emerge. And beneath it all, quantum rules continue to operate quietly, consistently, and without exception. They do not announce themselves. They do not demand attention. They simply shape what is possible. In doing so, they provide one of the most durable frameworks ever constructed for understanding nature. Not because they remove mystery, but because they locate it precisely. What remains unknown is bounded. What is known is reliable. That balance is the signature of mature science. Quantum physics, approached with patience, reveals itself not as a collection of paradoxes, but as a disciplined way of describing a complex world. A world built from interactions rather than objects, from probabilities rather than certainties, from relationships rather than absolutes. And within that world, stability arises not in spite of uncertainty, but because of it. This is where the account rests, not with a conclusion, but with a framework that continues to hold, quietly supporting everything that follows. With most of the structure now in place, the remaining space is best used to let the ideas breathe rather than to add weight. At this stage, clarity comes from calm repetition, from seeing the same principles appear in different settings without strain. Quantum physics, taken as a whole, does not claim that reality is unknowable. It claims that knowledge has form. That form is probabilistic, relational, and constrained. A quantum state does not catalogue everything that exists. It summarizes what can be predicted about outcomes of interaction. This distinction is subtle, but it matters. It prevents the theory from overreaching. It keeps description tied to testable consequence. This restraint is one reason the theory has endured. It avoids speculation where evidence cannot reach. Where questions cannot be answered, it remains mathematically silent. Silence, in this context, is not ignorance. It is discipline. As the theory matured, physicists learned to trust this discipline. Instead of forcing interpretation, they refined calculation. Instead of demanding pictures, they accepted structure. This shift did not weaken understanding. It strengthened it. Over time, the language of quantum mechanics became familiar. Terms like state, operator, and observable settled into use. Their meaning became precise through application rather than analogy. This precision allowed quantum theory to expand into new domains. Chemistry, materials science, and information theory absorbed its principles without friction. Each field adapted the language to its needs. In doing so, quantum mechanics became less of a standalone subject and more of a foundation. Foundations are not always visible. They support without drawing attention. They define limits without announcing them. The same is true here. Many modern technologies depend on quantum behavior without referencing it explicitly. The rules are embedded in design rather than explained anew. This embedding is a sign of maturity. When a theory becomes infrastructure, it has proven itself. At the same time, infrastructure must be maintained. Boundaries must be monitored. Assumptions must be tested. Quantum physics continues to undergo this process. High-precision experiments probe its limits. So far, it is held. Where discrepancies appear, they are examined carefully. Some vanish with improved measurement. Others hint at new effects. This vigilance keeps the framework alive. It also shapes how uncertainty is viewed. Uncertainty is not failure. It is a quantified feature. It appears in equations, predictions, and error bars. By formalizing uncertainty, quantum mechanics transforms it into a tool. It allows confidence to be expressed precisely. This precision is not aesthetic. It is practical. It allows decisions to be made rationally under constraint. In this way, quantum mechanics aligns with a broader scientific ethic. Claims are limited. Confidence is measured. Conclusions are provisional. This ethic is often misunderstood as hesitation. In reality, it is strength. Returning once more to the central themes, the pattern becomes clear. Interaction lies at the heart of description. Systems do not exist in isolation. Their properties are defined through relation. Probability encodes possibility. It does not hide ignorance. It structures expectation. Constraint shapes outcome. Laws limit behavior in ways that create stability. Emergence bridges scale. Small rules generate large patterns. These themes recur whether discussing electrons, materials, or the universe itself. They also apply beyond physics. Complex systems in many fields exhibit similar behavior. Local uncertainty coexists with global order. Quantum mechanics provided one of the first rigorous demonstrations of this principle. It showed that lawfulness does not require predictability in detail. It requires consistency across context. As this understanding settles, the early drama surrounding quantum theory fades. What once seemed shocking becomes simply different. The world described is not less real. It is more nuanced. It accommodates ambiguity without collapsing into chaos. It supports structure without demanding rigidity. In this balance, quantum physics finds its place. As the final portion of this account unfolds, there is no need to resolve remaining questions. Resolution belongs to experiment and future theory. What can be offered is orientation, a way of thinking that remains grounded even as concepts stretch intuition, a framework that respects limits while enabling discovery. Quantum physics explained slowly does not rush to conclusion. It allows understanding to form through repetition and coherence. In that coherence, the theory reveals its character, not mysterious in intent, not arbitrary in rule, not fragile in application, but careful, constrained, and enduring. And so the account reaches its final cadence, not by closing a door, but by settling into a steady rhythm. A rhythm defined by interaction, probability, and structure. A rhythm that continues beneath every scale, from the smallest excitation to the largest pattern, quietly, consistently, and without pause. As the remaining space narrows, the emphasis naturally becomes one of balance. Nothing essential needs to be added. What remains is to allow the structure already described to settle into a single, steady perspective. Quantum physics does not describe a universe that is fragile or unstable. It describes one that is carefully constrained. Those constraints do not prevent complexity. They enable it. At the smallest scales, rules restrict what states are possible and how they can change. At larger scales, those same restrictions channel behavior into stable patterns. Order is not imposed from outside. It emerges from limitation. This is one of the quieter lessons of the theory. Freedom without constraint leads to noise. Constraint without freedom leads to rigidity. Quantum mechanics sits between these extremes. Particles are not free to occupy arbitrary states. Fields are not free to fluctuate without limit. Measurements are not free to reveal everything at once. Each restriction shapes what can persist. From these restrictions, structure arises. Atoms form because only certain energy configurations are allowed. Molecules form because shared states lower energy. Materials acquire properties because collective arrangements stabilize. None of this requires intention or direction. It follows from rule. When viewed this way, probability becomes less unsettling. It is not the absence of law, but its expression across many possibilities. The theory does not abandon prediction. It refines it. Prediction becomes a matter of expectation rather than certainty. Outcomes cluster where structure allows them to cluster. This clustering explains why the world feels reliable. Chairs remain chairs. Clocks tick regularly. Planets return to their positions. The quantum rules underlying these behaviors do not conflict with them. They support them. At times, quantum mechanics is described as counterintuitive. This is often true. But intuition itself is shaped by scale. Human intuition evolved in a regime where averaging dominates. It is tuned to classical patterns. Quantum physics asks intuition to stretch, not to disappear. It asks for a broader frame. Within that frame, the behavior of small systems becomes coherent rather than strange. Superposition reflects the coexistence of possibilities. Entanglement reflects shared constraint. Uncertainty reflects trade-off. Each concept follows from the same mathematical structure. This unity is one of the theory's strengths. It does not rely on special cases. It applies the same rules everywhere. The difficulty lies not in inconsistency, but in unfamiliarity. Over time, unfamiliarity fades. What remains is method. Quantum mechanics teaches careful reasoning under uncertainty. It teaches respect for limits. It teaches patience with incomplete description. These lessons extend beyond physics. They inform how complex systems are approached in other fields. They encourage probabilistic thinking. They discourage overconfidence. In this sense, quantum physics has influenced scientific culture as much as scientific content. As the account nears its end, it becomes clear that no single image captures the theory. It is not best understood as waves, particles, or even fields alone. It is best understood as a set of rules governing how descriptions relate to outcomes. Those rules are abstract, but their consequences are concrete. They govern how matter behaves, how energy flows, how information spreads. They shape the universe quietly. The fact that these rules can be written compactly yet apply universally is remarkable. It reflects a deep simplicity beneath apparent complexity. Whether that simplicity is final remains unknown. Future theories may reveal deeper layers, but whatever lies beneath must respect what has already proven reliable. Quantum mechanics has earned its place not through elegance alone, but through endurance. It has been tested across scales, conditions, and technologies. It has adapted without fracture. Its remaining questions are not signs of weakness. They are markers of reach. A theory that explains only what is known leaves little room to grow. A theory that reaches beyond invites exploration. Quantum physics does the latter. As this slow explanation concludes, what remains is not a set of answers, but a way of seeing, a way that recognizes that certainty is contextual, that structure arises from constraint, that stability emerges from interaction, and that knowledge advances not by eliminating uncertainty, but by understanding it. Within that understanding, the quantum world becomes not distant or alien, but foundational. It is not separate from experience. It supports it. It does not disrupt order. It enables it. And in doing so, it provides one of the most reliable guides yet developed for navigating the deep structure of reality. This guide does not promise finality. It offers continuity. It does not insist on conclusion. It allows the account to rest, complete not because nothing more can be said, but because what has been said now fits together, quietly, consistently, and without strain. In a penultimate view, it becomes useful to step back once more and consider what quantum physics ultimately provides, not as a collection of results, but as a way of organizing understanding. At its core, quantum mechanics is a theory of relationships. It describes how systems influence one another, how information is exchanged, and how outcomes become fixed through interaction. It does not insist that properties exist in isolation. It insists that properties emerge in context. This emphasis on context resolves many apparent tensions. A particle does not need a precise position and momentum at all times, because those quantities only become meaningful through specific interactions. A system does not need a single definite state independent of its surroundings, because its behavior is defined through coupling. Seen this way, the quantum world is not incomplete. It is conditional. Conditional descriptions are not weaker than absolute ones. They are more flexible. They allow the same system to be described accurately in different situations without contradiction. This flexibility is essential for a theory that spans so many scales. The same rules describe electrons in atoms, currents in materials, and fluctuations in the early universe. What changes is not the rules, but the context in which they are applied. Quantum mechanics therefore operates as a framework rather than a narrative. It does not tell a story about what must happen. It provides a structure within which many stories are possible, each constrained by probability and interaction. This framework has proven resilient. When new phenomena are discovered, they are incorporated by refining states, operators, and interactions, not by discarding the core principles. The mathematical language absorbs novelty without losing coherence. That resilience is rare. Many theories succeed briefly before fragmenting under extension. Quantum mechanics has done the opposite. It has become more unified as its scope has widened. One reason for this is its economy. A small set of principles governs a vast range of behavior. Superposition, linearity, and probabilistic measurement are sufficient to generate complexity across domains. Another reason is its humility. The theory does not claim more than it can justify. It does not promise access to hidden mechanisms. It promises reliable prediction within defined limits. Those limits are clearly marked. Certain questions cannot be answered simultaneously. Certain transformations cannot be performed. Certain measurements cannot be combined. These restrictions are explicit. Rather than seeing these as shortcomings, modern physics treats them as guides. They define where effort should be directed and where expectation should be tempered. This attitude has practical consequences. It leads to careful experimental design. It encourages redundancy and verification. It prioritizes error analysis and uncertainty quantification. In this way, quantum mechanics has shaped scientific practice as much as scientific content. It has also influenced how reality itself is conceptualized. The idea that the world is fundamentally relational rather than object-based has echoes in other disciplines. Networks, interactions, and flows replace isolated entities. This shift does not dissolve reality. It redefines it. Objects remain useful concepts at appropriate scales. They are stable patterns of interaction. Their persistence reflects environmental reinforcement rather than intrinsic isolation. The same applies to laws. Laws are not commands imposed on matter. They are regularities that persist because alternatives are excluded by constraint. Quantum physics reveals this exclusion with unusual clarity. It shows how much of what feels necessary is actually selected. Selected by energy minimization. Selected by symmetry. Selected by stability under interaction. From this selection arises the familiar world. As the account approaches its final movement, it becomes clear that quantum mechanics does not need embellishment to remain compelling. Its interest lies not in strangeness, but in consistency across extremes. It connects the smallest measurable excitations to the largest observable structures. It links laboratory experiments to cosmic background radiation. It ties information processing to space-time geometry. Few theories achieve such reach without collapse. This reach does not imply completeness. Open questions remain. The nature of quantum gravity, the origin of space-time, and the ultimate limits of information are not yet settled. But these questions sit at the edge, not the center. They do not undermine the framework. They point beyond it. That distinction matters. The penultimate position is therefore one of orientation rather than resolution. It situates quantum physics within the broader landscape of knowledge without forcing closure. It shows how the theory holds together, how its parts reinforce one another, and how its limitations are as informative as its successes. In this view, quantum physics is neither mysterious nor mundane. It is precise where precision is possible and restrained where it is not. It offers a disciplined way of describing a world that is complex without being chaotic, uncertain without being arbitrary, and structured without being rigid. With that orientation established, what remains is not explanation, but rest. In the final movement, there is no need to resolve what remains unresolved. Quantum physics does not arrive at a single closing statement about reality, and neither should an account of it. Its strength lies in how well it holds together without forcing completion. What it ultimately offers is a disciplined framework for describing how the physical world behaves when examined closely. It replaces certainty with constraint, intuition with structure, and narrative with rule. In doing so, it remains consistent across situations that once appeared incompatible. The theory does not claim that reality is vague. It claims that description has limits. Those limits are precise. They are written into the mathematics and confirmed by experiment. They tell us what can be known together, what must be traded off, and what remains probabilistic. Within those limits, prediction is remarkably reliable. Quantum mechanics does not drift. It does not depend on interpretation to function. Its calculations succeed regardless of philosophical stance. This independence is rare and valuable. Over time, the apparent strangeness of the theory fades. What remains is a quiet familiarity. Superposition becomes a rule for combining possibilities. Entanglement becomes a rule for correlation. Measurement becomes a rule for updating description. None of these require metaphor. They work without appeal to imagery. They operate through consistency. This consistency allows quantum physics to sit comfortably beneath other theories. It supports chemistry without replacing it. It supports materials science without redefining it. It supports cosmology without dictating its narrative. Each field draws what it needs and leaves the rest intact. In this way, quantum mechanics functions less like a story about the world and more like a grammar. It defines how statements about physical systems can be formed and related. It constrains expression without dictating content. Grammars do not describe meaning directly. They make meaning possible. The same is true here. Quantum physics does not tell us what reality feels like. It tells us how descriptions must behave if they are to remain consistent with observation. That modesty is part of its durability. As understanding advances, new layers may be added. Deeper structures may be revealed. The language may be extended. But the core principles will remain embedded, shaping whatever follows. Just as classical mechanics persists within quantum mechanics as a limiting case, quantum mechanics will persist within any future framework that succeeds it. This continuity ensures that knowledge accumulates rather than resets. In that sense, quantum physics explained slowly does not end with a conclusion. It settles into position. It becomes a background structure, quietly supporting explanation without drawing attention to itself. The universe it describes is not theatrical. It does not hinge on observation or collapse for effect. It unfolds according to constraint and interaction. Particles are not mysterious agents. They are excitations. Fields are not abstractions. They are structure. Information is not secondary. It is physical. From these elements, everything else arises. Atoms bind. Forces balance. Patterns stabilize. Complexity becomes possible. Nothing in this account requires drama. Its coherence is sufficient. And so the explanation ends where the theory itself rests, not with certainty, not with paradox, but with a framework that holds. A framework precise enough to guide experiment, flexible enough to absorb discovery, restrained enough to respect limits. Quantum physics, approached patiently, reveals itself not as a puzzle to be solved, but as a structure to be understood. And once understood, it remains. Quietly, consistently, doing its work beneath every scale of the world.